All right, now let's have a look at these problems here. So this problem here comes to us from a node Armel. Suppose that these 2 points, A3, 4, and 7, 10, are opposite vertices of the rectangle ABCD. Vertices B and D must therefore lie in a circle with the equation blah, where these are all real numbers. Compute the order triple PQS. Okay, so we're told that this is going to be a circle, so let's go ahead and sketch this out. There's going to be some circle in the coordinate plane, not exactly where, not exactly sure where. We have this here, and we're going to have something that looks like this here. Now, of course, the sides of the rectangle may not necessarily be parallel to the axes, and that's okay. This is going to be A, 3, 4. Here's B, we don't know what that is, and C is going to be at 7, 10. And then D is going to be, we don't know what that is either. That's okay. So we have to determine something about this here. These are opposite vertices of the rectangle. So if you think about what's going on here, it makes perfect sense here for us to consider that the center is going to be exactly the intersection of the intersection of the diagonals, right? If I were to draw the diagonals like this, AC, DB, this point here, let me call it O. Remember that the diagonals of a rectangle bisect each other, and the diagonals of a rectangle are congruent. So that means OD, OC, OB, OA are all the same distance. So as a result here, it makes sense that this should be the center of the circle here. So that means we can find the location of O. It's just the midpoint of AC here. So that's just 3 plus 7 over 2. And 4 plus 10 over 2. So this is going to be 10 over 2, comma 14 over 2, which is 5, 7 here. So now we know the center of the circle is 5, 7. And that's great, because that gives us what we need. We just now need the radius. And the radius is easy, because it's just the distance between this point and anything here. So we just solve for this case here. Let's look at OA. The distance here is just going to be 5 minus 3 all squared, plus 7 minus 4 all squared, which in this case is 2 squared plus 3 squared, or let's see, 4 and 9, which yields us radical 13 here, okay? So that means, now that we have the radius here, we have these two critical pieces of information. There's a center and there's a radius here, so now we can write the equation of the circle. The equation of the circle here is going to be x minus 5 squared plus y minus 7 squared equals radical 13 squared. Well, that's just 13. Now that's great, but the problem didn't ask for it. The problem asked for it in this form, which means I have to unpack the boxes and shove everything to one side. So let's see, that's just algebra. So let's see, x minus 5 is just x squared minus 10x plus 25 here, right? So because we have an x squared, we have a minus 5x and another minus 5x, and then we have the positive 25 here. Same thing with y minus 7, we get y squared minus 14y plus 49, and that's equal to 13 here. So now it's just a matter of gathering all the terms. We get x squared minus 10x plus y squared minus 14y, and that's, let's see, this is going to be plus 25 plus 49 minus 13. So it's going to be x squared plus y squared minus 10x minus 14y. 25 plus 49 is 25 plus 50 is 75 minus 1 is 74. 74 minus 13 is 61. This is all positive here. And we note that this matches with the form here, right? So now it's pretty easy to read what this is. So therefore the order triple here is just minus p, so that's 10. Q is 14. And S is 61 here. So that's number 2. Okay, number 4. Determine the smallest possible distance between a point in the graph of blah and a point in the graph of this. Okay, so again, note that we were given these things here, so we're going to go ahead and complete the square and figure this out here. So let's go ahead and do that. So in this case here, we have this off, so let's write it out here. We have x squared plus 6x plus y squared minus 8y equals 0 here. So this circle 1, I'll call this circle P here, circle P, I guess. Again, we have, this is double the constant, so positive 6 is double your constant, so positive 6 divided by 2 is a positive 3, and you square that, you add 9. So we have a plus 9 here, which we add 9 to this side. Same thing over here, net negative 8 is double the constant, so the constant's negative 4, we add 16. Okay, so then that means this becomes x plus 3 squared plus y minus 4 squared equals 0 plus 9 plus 16, which is 25. Okay, that's really helpful here, because now we know the center, so P is going to be at the point negative 3 comma 4, and the radius of P is going to be 5. And now we're going to do the same thing for the other one here, okay? So again, I'll do the same thing, x squared minus 14x plus y squared plus 10y. Note the 65, I'm going to shove that to the right-hand side. I'm going to make it a minus 65. And you note that I made some spaces here, because you know, in this situation, we're going to be adding constants here. So again, the same thing, negative 14 is double our constant, so the constant is negative 7. We add that squared, which is 49. We add 49 here. Positive 10 is the constant squared, so 10 divided by 2 is 5. We square that, add 25 here. Alrighty, so this becomes x minus 7 squared plus y plus 5 squared equals, let's see, negative 65. Negative 65 plus 25 is a negative 40. Negative 40 plus 49 is 49 minus 40, which is 9. So if there's a circle Q here, Q is going to be at the point 7 comma negative 5, and the radius of Q is going to be 3. Okay, so now we're going to go ahead and take a look at the picture here. We're going to try to sketch what this looks like. So let's draw this out. Here's x, here's y. Now, P is at negative 3 comma 4 with a radius of 5. So it looks like this here. Here's P, and our circle is going to look something like this. Right? Q is going to be at 7, negative 5, like this, and has a radius of only 3 here. So we have a circle that looks like this. Now, I think you can intuitively see here that these circles are not going to intersect. And in order to be sure about this, I guess the first and most important thing is make sure that the circles don't intersect here. So what's going on here, let's take a look at what's going on here. So one thing to make sure that the circles don't intersect is for us to calculate the length of PQ here. So let's go ahead and calculate the length of PQ. PQ, right, that's just the distance formula here. This is going to be, let's see, well, this is negative 3, 4 to 7, 5. That's going to be 7 minus a negative 3 all squared plus negative 5 minus 4 all squared, which is the square root of 10 squared plus 9 squared, which I believe is radical 181. That means the distance from P to Q here, this distance here, is root 181. Now, we want to determine the smallest possible distance here. So it makes sense that if this entire thing is radical 181, if we want the distance between the 2 points to be as small as possible, we got to pick the points that are sort of closest to one another. In particular, if you note that this point here, where this circle intersects this green line segment here, this particular point here, let's call it A, right? PA has a distance of 5 because it's the radius of the circle. By a similar token here, if we call B the intersection of the green line segment and circle Q, BQ has a length of 3 here. Now these are pretty close to one another. In fact, they are the closest that we can make. And AB here, well, that's easy because there's just AB here is just going to be the distance, which is radical 181 minus the two quantities, 5 and 3, the radii. So that yields us radical 181 minus 8, and that is the smallest distance that we can generate between these 2 points. Number 5. Now, this is a problem of my own creation. This one here, I'm actually particularly proud of this one. But let's go ahead and sketch this out and try it out. So the lines y equals 1 and the circle x squared plus y squared equals 2 divide the coordinate plane into several regions, 2 of which have a finite area. Compute the area of the smaller of the 2 regions. Now, again, we note here, here's our axes. I'm going to draw this. This is pretty straightforward here, right? X squared plus y squared equals 2 is a circle. The nice part about it is that's centered at the origin and has a radius of radical 2 here. So we're going to get a circle that looks like this. So again, I'd like you to ignore the black for now and just focus on the blue. This is x squared plus y squared equals 2. Now, we also have the line y equals 1, and that's going to go something like this here. Bang, like that. Now, it makes sense here since 1 is less, so this point here is 0 comma radical 2. Since 1 is less than radical 2, it makes sense that this line here is going to hit the circle in 2 places. I'm going to call the points here A and B. Now, where do they hit it? Well, let's see. We know y equals 1, so we might as well go ahead and do that here. So we get x squared plus 1 equals 2. So x squared is equal to 1, and that actually gives us 2 things. X is plus or minus 1 here. So that actually gives us 2 points. This is the point 1, 1, and this is the point negative 1, 1. Okay? So we know that there are actually 2 finite areas. So there's one region, which is sort of the outside of the circle here, that has infinite area because it goes on forever. However, if we ignore the axes here, we actually have 2 things. We have the bigger portion of the disk and this small wedge up here. So essentially what we're doing is we're finding the area of this sort of shard. I'm sorry, I meant a shard here. All right, so maybe we can determine something here. Here's point O, the center of the circle here, right? Now, in this case here, if we take a look at what's going on, note that this is negative 1, 1 to 0, 0. So that means the slope of this is negative 1, right? The slope of AO is negative 1. And here the slope of this is positive 1. No, wait, negative 1 times positive 1, that's negative 1. That means the slopes have a product of negative 1, which means there's a right angle here. And furthermore, these are radii, so these are the same. So we know that triangle AOB is therefore 45, 45, 90, right? That's really helpful. And because that's 90 degrees, this means that this entire thing, now we know that our goal, this, is going to be equal to this thing here, right? And I know I'm drawing this really badly, ladies and gentlemen. This sort of wedge here minus triangle. Now the triangle is quite nice because, again, we know that's 45, 45, 90. So let's go ahead and write this one out here. This is a circle. It's a quarter of a circle, in fact, because that's 90 over 360. 90 over 360 times the radius times pi times the radius squared, and the radius we know is radical 2 from this. And the area of this triangle, it's a 45, 45, 90 triangle, and the legs are radical 2, so it's going to be 1/2 times radical 2 times radical 2. So now it's just a matter of putting it all together. This is a quarter times pi times 2 minus 1/2 of 2. So we can put it all together, and we get pi over 2 minus 1. And that is the area of the smaller piece that we wanted.